So I've tried to make this point a couple times as we've been going through polar. And I think an important connection to old stuff, polar really is just a different type of parametric, right? So we've been looking at parametrics and vectors. In both cases, x's and y both depend on t. With polar, x's and y's really will end up depending on theta. So it's just a different parameter for the x's and the y's. So we did finish last time talking about dy dx, and this statement right here is super duper important because there's going to be all types of different derivatives that we're going to see. I guarantee you there's going to be a time when we look at dy dt and we try and figure out what it means. There's going to be other times when we look at dx dt and say, hey, what does that mean? There are going to be other times when we look at dr dt and say, what does that mean? None of those things are the slope of the tangent line. The only thing that's the slope of the tangent line is dy dx. Okay, so please don't have flawed thinking and thinking that, hey, any derivative I do will be the slope of the tangent line. It will be a rate of change, no doubt, but the slope of the tangent line, always dy dx. Okay, cool. So in order for us to develop this, what we did last time is we said x is equal to r times which trig function? Cosine theta. It's one of those key conversions. And so y is equal to r sine of theta. And following the parametric nature of polar, dy dx would then equal dy d theta over dx d theta. Okay, so then to fully develop this a little bit further, what we'd want to do is find dy d theta and dx d theta, realizing that the r is either going to be a constant or, in just about every other case that we're going to look at, pretty much every case I think, r is going to be some function in terms of theta. Okay, so in order to find dy dx, what we'd have to do is use the product rule a couple of times. So dy dx equals, dy d theta would be 1d2 plus 2d1. So that would be r cosine of theta. So there's 1d2 plus 2 d1. Again, let's keep in mind that r is just going to be some function in terms of theta. So r prime is going to be blah, blah, blah theta. And then the denominator would be dx d theta. So 1 d2 plus 2 d1. Again, r is in terms of theta, so r prime would be in terms of theta as well. I think I mentioned at the end last time, you know, if you are like a hyper formula memorizer, maybe you memorize this. I don't, like me personally, this is like totally a me personally thing. I have never memorized this. Sure, if I took a few minutes I could, but I've always just developed it really quick because I can do a product rule fast, and it feels for me like the right thing to do to just develop it each time. You make your own decision about what you want to do. But even if you do memorize it, make sure you know where it comes from, because if you don't and you forget, you won't be able to redevelop it. Okay, so just remember where it comes from, and whether you choose to memorize or not, you should be served well. Okay, so do you guys have any questions on that? Do you see how a polar slope of the tangent line can get kind of complicated? You see how this could grow to be pretty large amounts of stuff pretty easily. Okay, so if there's no questions, we will move on. I got a couple questions for you, I think. Yes. Okay, so like we talked about a lot with those graphs last week, what might cause or what could cause a horizontal tangent line? How would you express that? If you're looking for a horizontal tangent line, if you think about it, so many of these graphs do have horizontal tangent lines, right? Say again?
The slope of the line is 0.
The slope of the tangent line is 0. Okay, so that is definitely correct. Let's dig a little bit deeper, like in terms of what we just talked about. If dy d theta equals 0, I agree that's going to be a... And dx d theta doesn't. Yes, there it is. So isn't this just like that parametric stuff we did? It's just instead of dx dt and dy dt, it's dx dy of d theta. Yeah, so if dy d theta is 0, dx d theta is not, then that's going to be a horizontal tangent line. What do you think about a vertical tangent line? Just the other way. Yeah, so that would be if dx d theta is 0 and dy d theta is not. Okay, so if both, so if dy d theta and dx d theta are simultaneously 0, then no conclusion can be drawn about the tangent line. I'd say frequently it's going to be one of those sharp point things, but you can possibly have a point of discontinuity and other things like that. So that might not always be the case. Yeah, if you think back to like the cardioid that we did, that has that little sharp point in there, I think you're going to find both dy d theta and dx d theta are 0 at that particular angle. Okay, all that makes sense. I'm hoping that you're making good connections back to the stuff that we've already kind of established. All right, well, let's do our example here. Number 2 says if r is equal to that, find locations. I remember this. Locations are a little vague. Let's do this. Let's instead of the word locations, let's say find angles. Angles for all horizontal and vertical tangents. Okay. You guys need some direction on this, or looks like you're starting to roll? Okay. It's based on what we just did. So let's review really quick. If you're working, go ahead and work. If we're looking for a horizontal tangent line, we want to look for where dy d theta is 0 and dx d theta is not. So we would want to have an equation for dy d theta and an equation for dx d theta. The key for this is getting, like right now, our graph is in terms of r and theta. We want it to be x in terms of theta and y in terms of theta. So I think the first thing I would do is write y is equal to, if it's okay with you, I'll distribute 2 minus 2 cosine theta times sine of theta.
And how does r?
That is r.
That is r.
Why is r?
R is 2 times 1 minus cosine theta.
R equals that.
He's
Oh, why?
Y equals r sine theta
Oh,
Wow.
y equals r sine
from
theta.
before,
R is the equation.
and r is the 2 minus 2 cosine theta. Does that make sense now? Okay.
I know what.
And then we do the exact same thing for x. So x would equal 2 minus 2 cosine of theta times cosine of theta. So that's just r sine theta and r cosine theta. Okay, now it looks like you guys are really off and running. Am I right? If you want, we'll do this at some point in here. If you're interested, you certainly could graph 2 minus 2 cosine theta. I've supplied that little graph over there, of course, for you to kind of use in conjunction with your work. And if you don't do that, we'll do that at the end. I think that's a valuable thing. Would equal, it's going to be a product rule. So I'll try to fit this on the page here. So it's going to be 1 d2 plus 2 d1, and d1 is just going to be 2 sine of theta. Make sense? So, yeah, I'll just do it like this. So 2 sine of theta. I'm going to clean this up just a little bit by distributing and doing some multiplying. So I'm going to get dy d theta equals, let's see here, it's going to be 2 cosine theta minus 2 cosine squared of theta plus, plus 2 sine squared of theta. So did you guys get there?
Yeah.
So if you got there, that's a really good thing. You're on the right track.
Do you have to simplify that for the
So-
test?
So there's something we need to do here. You know, McKenna's asking about the AP test. I can't say for certain which way they would go with this year. I know that in the past I have seen a question sort of kind of like this. So, you know, we don't want to look at this and say that'll never happen. But at the same time, this is not like a tried and true, this is always on the free response sort of thing. So here's what it is. If you look at what's left over there for dy d theta, and by the way, we want to set dy d theta equal to 0, don't we? Probably should have done that right at the start once I found dy d theta. But if you look at the three terms in dy d theta, I've got a cosine squared, and a sine squared. And so this equation as it stands, at least without a calculator, is, at least I'm not sure, maybe there is a way to solve it in its current form. We're going to have to change the form a little bit to make it into a solvable form. And the way that I would think of it is, one of those things is not like the other one. Sine squared, right? There's two cosines over there, two cosine terms. One of them is a sine term. We need to figure out a way to get rid of the sine squared and replace it with something in terms of cosine. Using the Pythagorean identity, that's exactly what we would do. So I would say then 2 cosine of theta minus 2 cosine squared of theta plus 2 parentheses 1 minus cosine squared theta equals 0. So that's a major step, right? That's a key step, substituting in with the Pythagorean identity, and that's going to be kind of the key for us moving forward. If we don't do that, I think the moving forward is probably not going to happen. Okay, so I'm going to distribute, and when I distribute, I'm going to distribute and rearrange a little bit. Aren't I going to end up with negative 2 cosine squared to go along with the other negative 2 cosine squared? So I'm going to write that down as negative 4 cosine squared of theta. And then I'm still going to have plus 2 cosine of theta. And then 2 times 1 is 2. So it'd be plus 2 is equal to 0. I tried to do this really nicely for you. What is that thing? Negative 4 cosine squared, blah, blah, blah.
Oh, that's the
It's a quadratic. It's a quadratic. We'll call it an ultraviolet quadratic. How about that? Yeah, I'm going to erase this, but isn't this essentially no different than negative 4x squared plus 2x plus 2 equals 0? Yeah, the input is not just an x, it's a cosine, but isn't it the exact same pattern? You probably saw this in pre-calc, yes? Okay. So, or probably in Algebra 2, Algebra 1 as well. What might you do to make the numbers just a touch easier? Do what?
Take out a 2.
Take out, couldn't we, since it's an equation equal to 0, couldn't we just divide everything through by 2?
Yeah.
So I would do that. And as a matter of fact, maybe we should divide everything through by negative 2 to make sure your a value is positive. I think I'd do that. So 2 cosine squared of theta minus cosine of theta minus 1 equals 0. And now the goal is to factor this. And if this is going to factor, let me just give you a hint about this. If this is going to factor, doesn't it have to factor like this? 2 cosine of theta plus or minus something times cosine of theta plus or minus something equals 0. So start there and figure out what the other two numbers would have to be. Because if it is going to factor, nicely at least, it's going to have to factor like that. So what do you think? What number goes where? Because it does factor.
Plus 1 minus 1.
Yep, I agree. In that order. Plus 1 there, minus 1 there. Can you see now how we're almost at the end? It's been a long journey, but we're almost there. Set each factor equal to 0 and solve. So this would be cosine of theta equals negative 1/2. This would be cosine of theta is equal to 1. And here's where, did any of you guys graph this ahead of time? Here's where maybe graphing it ahead of time would be helpful. So maybe do this now. If you graph this, you can, you should be able to figure out the domain for theta to get this traced exactly once. That makes sense? Be able to see what graph it is and start to predict horizontal and vertical tangents, that kind of thing. Okay, so with that as a graph, did you guys notice what kind of a domain you needed to get this graph down? Did you need like 0 to pi, 0 to 2 pi? 0 to 2 pi, yeah. A lot of, once you move away from the roses and the lemniscates, most of them are 0 to 2 pi. most of the classic ones. Okay, so then the reason why that's helpful is because as we try to solve these two equations, this would like limit the number of angles that we're going to get. We're not going to go beyond 0 to 2 pi. So cosine of theta equals negative 1/2. What angles have a cosine of negative 1/2? They're going to be pi over 3s, aren't they? Yep. And they should be in the second and third quadrants. So 2 pi over 3, 4 pi over 3. Those seem to make sense. You guys good with that? And then where is cosine of theta equal to 1? Bless you. So 0 and 2 pi, 4 pi, so on and so forth. We'll stop at 0 only because we don't want to retrace it over to 2 pi. Although if we did, it's not necessarily wrong. We'd just be listing the same angle twice. All right, so let's look at the graph here. Let's see what we see. So 2 pi over 3, of course, my graph is not perfect. 2 pi over 3 would be there. I'd say my graph is actually reasonably good. That looks about like where you'd have a horizontal tangent, doesn't it? And then 4 pi over 3, so right there and right there. So horizontal tangents there and there. Whoops. Seems pretty reasonable, doesn't it? What about theta equals 0? Facing straight right. Doesn't that seem a little less likely? What do you see right there? Looks like a sharp point, doesn't it? And so if that really is a sharp point, then what's going to happen when we do dx d theta? 0 will probably show up again, won't it?
Yeah.
Probably. So let's see if that happens. I just show you the graph there just so you can kind of get a basic idea of the graph. And now we'll try to prove our theory. And by the way, how many angles, based on the graph, how many angles do you guys see where the tangent line is vertical? 3 different angles. And probably the 2 angles on the right, it's probably going to be the same equation of the tangent line, but it'll be 2 different angles. We'll investigate this a little further. Okay, so I am going to try to navigate this little narrow space here. I don't know, we'll see how this goes. So I'm going to say we got to do dx d theta now. Just draw a little line right there. So dx d theta is going to be another product rule. So 1d2 plus 2d1. So, well, I don't know. Maybe it'd be easier to do it this way, space-wise. Let's do this. Could we distribute that cosine real quick? So if we do that, it's x equals 2 cosine of theta minus 2 cosine squared of theta. By doing it that way, that eliminates the product rule, but it does bring into play chain rule. I don't know. Pick your poison. Got to do one or the other. Pick your candy. Maybe that'd be a better way to put it, right? Select your candy. Chain rule or product rule. I'm going with chain rule. Okay, so here we go. Dx d theta is equal to this. And let's see here. You got to multiply by the derivative of the inside. And so I think all that's going to do is just change that sign to a positive. -4. Yeah, okay. That makes sense? Okay, so we're going to set that equal to 0 and try to solve. And thank goodness, the solving on this is going to be a touch easier than the other one. What strategy do you guys see? We do have a mix of sines and cosines, kind of like the other one, but what more common, more elementary strategy will work here? Yeah, the goal really is just to create a product, and by factoring out a sign, we can create sine of theta, we can create that product. So I would say sine of theta factored out would give us -2 plus 4 cosine theta equals 0. The fact that there's no squareds in that derivative makes this a little bit easier as compared to the other one. So it's at this point we set each factor equal to 0. So where is sine of theta 0? Zero and pi. Exactly right. So as predicted, we see this showing up, don't we? We see that theta equals 0 showing up for being zeros of both dx d theta and dy d theta. So perhaps that sharp point idea makes sense. And then, oops, at what angles is cosine of theta equal to 1/2? Yeah, so basically the first and fourth versions of the other ones we had, right? So theta is equal to those, pi over 3, 5 pi over 3. Okay, so now we can start to draw some conclusions, but perhaps it would be good to check out the graph and see if these really do make sense. So looking at these two over here, theta equals 0, that's where we're going to get that sharp point from the cardioid. So I would say, based on the fact that theta equals 0 for both, we could cross those out. But then the pi, when you're facing straight right, that does look like a vertical tangent, doesn't it? And then when you look at pi over 3 is, I don't know, right in there somewhere. 5 pi over 3 would be right in there somewhere. I'm seeing vertical tangents there as well. And due to symmetry, it's probably the same line, just two different angles generating that line. So what we could do then is, based on our graph, based on our analysis, we could then draw our conclusion and say that we've got horizontal tangent lines at theta equals 2 pi over 3 and 4 pi over 3, vertical at theta equals pi over 3, 5 pi over 3. It's a doozy, isn't it? This would be one of the ones where you probably could show this to a pre-calc student and they would freak out a little bit, maybe, perhaps. I don't know. Not that we want to do that. You guys have any questions at all? Okay, so let me just give you a couple of pointers. I would say that this substitution we did over there, replacing sine squared with 1 minus cosine squared, and likewise, couldn't we replace cosine squared with 1 minus sine squared if the tables were turned a little bit? I would say that is a common thing. Please don't look at that and be like, oh, he gave us the hard version, but we'll never do that. Don't think that way. Okay, I would say that that's actually something that could happen. AP test, my quiz, AP, whatever. Yes, sir.
Because the tangent line for at theta equals pi over 3 and 5 pi over 3 is pretty much the same line.
It is the same line.
Would you say that there's 4 tangent lines or 5 tangent lines?
Well, you mean like
on the whole graph?
if we grouped vertical and horizontal into one big pile and said how many different lines are there?
Right.
So it depends on what you're being asked. If you said how many different lines have a vertical tangency relationship, or how many lines are vertical tangents to this graph, I would say that there's only 2 lines that are vertical tangents. But if it said how many angles on this graph produce a vertical tangent line, you have to say 3. Right? So it depends on if you're being asked for the angle that produces the vertical or horizontal tangent line versus what is the equation of the tangent line. Because you're right, pi over 3 and 5 pi over 3 based on symmetry, we can figure it out pretty quickly. It's just going to be x equals the same thing for both, right? But it's 2 different angles generating those. And really, if you think about it, on the curvy graph itself, there are 2 different places, right there and right there, that have vertical tangents.
Right.
2 different locations where the tangent line goes vertical, but it does happen to be the same equation of the line. Yeah. Does that make sense? Okay, cool. I kind of figured this would take about our whole time. It's a big one, isn't it?
Yeah.
Cool. Okay, so yeah, we'll cover the old tangent lines at the pole and all that stuff later.
Should I go?
Thanks, Blake. Yeah, you're good.
I have to go now.
Have a good one.